Hello everyone. So this is the live interactive session for week 8 of the course Structural Geology offered by NPTEL. And today's topic of discussion is folds and mechanism of folding. So this is the course outline and we have already covered 7 weeks. So this is the 8th week discussion session for the 8th week of content. And the topic of 8th week is mechanism of folding and superposition. So we have 4 live discussion sessions remaining, and today is 14th of September 2024, and the live session is being held from 4 p.m. to 6 p.m. and this is the Google Meet link to join this live session. So about today's live discussion session, so first I will brief about the content of week 8. So in week 8, we mostly learned about folds in structural geology and their geometrical aspects and their classifications, field observation and identification, and measurement of structural attributes of folds in the field. Then we also learned about the divergence of regional folds, folds in ductile shear zones, mechanisms of folding of rocks, buckling instability during folding, control of layer thickness and shear component on the fold patterns, flexural slip and flexural flow mechanisms of folding. Then we learned about the concept of deep isogon and orthogonal layer thickness, Ramsey's classification of fold based on deep isogon geometry. And then we learned about the superposition and interference of folds and Ramsey's classification of fold interference patterns such as type 0, type 1, type 2, and type 3. And then understanding regional deformation sequence by studying the fold interference patterns. So this was the overall content of week 8. And for today's discussion, we will mostly be solving conceptual problems related to geometry, superposition, and mechanism of folding. So without any ado, let us start today's problem solving session on folding and mechanism of folds. So the first question says, a bed is overturned if the dip of the axial planar cleavage and the dip of the bed are in option A, the same direction and the bed is steeper. Option B, the same direction and the cleavage is steeper. Opposite direction and the bed is steeper. And opposite direction and the cleavage is steeper. So this is a classic example of the fold divergence, the topic of fold divergence, and this is how we identify the hinge of a regional fold, because regional folds, as we see, so if we are reading some structural geology textbooks or even this course, we all see idealized folds, cylindrical folds, beautiful hand specimens. But the thing is, when we do structural mapping, it is quite impossible to visualize the regional fold because it can span up to hundreds of kilometers in areas. And in that case, just identifying the different exposures of the field, exposures of the fold in the field is quite challenging. And for that matter, we need to rely on some of the clues that we can directly observe from the geometrical relationship between the cleavage and the bedding plane of different exposures. And from that, we try to analyze the relative orientation of the hinge, the fold axis, the axial plane, the limbs, and different kinds of geometrical attributes of a fold. So in this case, the relation between the cleavage planes or the axial planar cleavage and the dip of the bed is important to understand in which direction the the hinge of the fold is lying. And one of the important relation that we also discussed in our previous live session is the vergence. Say for example, this is a limb of a fold. The hinge line could be here anywhere in this direction. We don't know that because say for example in a field outcrop, if this is a field outcrop, we are only getting this much of exposure. These are the bedding planes. And we find traces of the axial plane cutting across the bedding planes. So in this scenario, if we zoom into this part, we will find that the cleavage, axial planar cleavage, makes an acute angle and an obtuse angle with the layer or bedding plane. So in that case, the theory says the opening of the direction of the acute angle will tell us about the vergence. So this is applicable for normal folds. Normal in the sense that they are not sheared and they are not overturned, because an overturned fold will have a different geometry than a normal fold. So if I just see this schematic diagram on the screen, we will see that this is the normal scenario. So this is a normal fold, and this one is the overturned fold. So in a normal fold, we will see this kind of relationship that I have just drawn. In that case, the opening of acute angle will dictate the convex side of the hinge, and the opening of the obtuse angle will tell us the concave side of the hinge. So in this case, you will see that the axial planar cleavage is steeply dipping than the bed. However, if we overturn the limbs of a fold, then one limb will be gentler and one limb will be steeper than the axial plane, because we are providing an asymmetry into the system, and therefore one limb will be stretched and another limb will be shortened. right? So in this case, the shallower bed or the shallower limb will be having less steep deep amount than the foliation, or in other sense, for low dipping bed or the low dipping limb, the trace of the axial plane will have steeper dip than the uh, bedding plane itself. However, if we come to the steeply dipping bed or the forelimb, in that case we will see that the axial planar cleavage becomes shallower than the bedding plane itself. Okay, so this is the scenario for an overturned fold. In that case, both the bed and the axial plane will dip in the same direction, but the bed will be steeper. So option A is correct. And if I may write, in an overturned fold, axial planar cleavage and the beds dip along same direction. And for a normal scenario, we will see that in both of the limbs, the axial plane is steeper, always steeper than the bedding plane itself. But in case of an overturned fold, the bedding plane will be steeper in the overturned limb. So one limb is low dipping limb. So this is shallow dipping limb, and this one is the overturned limb. Okay. So this was about the first question. Now let us move up to the second question. So the question says, a set of cylindrical upright folds superposed by another set of non-coaxial folds. The axis of the superposed folds at any spot is determined by option A, fold dihedral angle of the first set of the folds, fold dihedral angle of the axial planes of the two sets of the folds, intersection of the axial planes of the two sets of the folds, and intersection of the limb of the first fold and the axial plane of the latter folds. So if we see this schematic diagram, we can immediately identify that type 1 and type 3, these are coaxial superposition, right? But type 2 is non-coaxial deformation. So if a set of cylindrical upright folds are superposed by another set of non-coaxial folds, that means we are talking about a type 2 interference pattern. Not interference. say superposition of cylindrical upright fold and another set of non-coaxial fold will lead to type 2 interference pattern. Okay, so this is the initial fold, and this is the axial plane, and this is superposed by another set of fold. And this is the axial plane. So if you see, the axial planes are perpendicular to each other. The intersection of two axial planes will provide us the second axis, of course, right? And this will be contained along the S2. This is the second foliation plane. This is S1, right? So if this is S2, then the second fold axis F2, it will both lie on S2 and S1. So we can say that F2 will lie on F2 will lie on both S2 and S1. However, due to the non-coaxiality of type 2 interference pattern, we will see that F2 and F1 are perpendicular. Okay, that means not only will they have different plunge, but also they will have different trend, right? That means F2 and F1 will have intersecting trend and plunge. Now the question says the first set of folds are cylindrical upright. That means F2, plunge of F2 is 0. Sorry, plunge of F1, P F1 is equal to 0. Then of course, plunge of F2 will be close to 90 degrees. That means it will be steeply dipping or steeply plunging fold axis. So in this case of interference pattern, so if this is fold generation D1 and this is fold generation D2, then the interference pattern that we will be seeing here will have a second generation fold which is steeply plunging. So the second generation fold axis will be the intersection between the initial axial plane S1 and the later stage axial plane S2. So therefore, at any point of the exposure, if we can find the angle between, or if we can determine the orientation of S1 and S2, then the intersection point will provide us the F2 axis in case of non-coaxial type of deformation. So option C is correct in this case, that the intersection of the axial planes of the two sets of the folds will provide us with the fold axis. The axis of the superposed folds will be estimated from this method, that is the intersection of the axial planes of the two sets of the folds. Okay, so moving on to the next question. Question number 3. In a fold, if the curvature of the inner arc is lower than the curvature of the outer arc, the deep isogon will be option A, converge towards the inner arc, option B, diverge towards the inner arc, option C, either converge or diverge, option D, remain parallel.
It will be converged towards inner arc.
Converging towards the inner arc. Okay, let us see. So curvature is lower for the inner arc, right? That means the fold will be like this. Now, if I draw the axial plane, this is like this. Now, if we see that what is deep isogon? So, deep isogon is the imaginary line that joins the points of equal deep among amongst intrados and extrados. So the formed surfaces of the fold are two different layers. These are called the extrados and the intrados, respectively. Now, since the outer arc has higher curvature, so the deep will be steeply changing. So, say for point A, we will have this, and point B, we will have this, Similarly, point C will have this, and point D we will have this. So to maintain the deep isogon, it has to diverge. The equal deep amounts, the deep isogons have to diverge away from the axial plane towards the inner arc. So in this case, option B will be correct. And what kind of fold it is? So class 1 folds are based on converging isogons, right? Class 2 means parallel isogons. Class 3 means diverging isogons, right? So if a fold has inner arc with lower curvature than the outer arc, the deep isogons will diverge and it will eventually form
Class
class 3 fold. Okay, moving on to the next question. A horizontal bed is folded in a manner that the axial plane of the fold is vertical and strikes north-south. If it is a non-plunging fold, the amount of dip of the bed in the hinge zone of the fold is 0 degrees, 30 to 50 degrees, 50 to 70 degrees, and 90 degrees.
it will be 0 degree
Are you sure?
or 90.
Exactly. It is. It can either be A or also D. Both options are correct because a fold can be like this with an axial plane here. So this is non-plunging fold with vertical axial plane. right? So this is your fold axis. However, the fold can also be neutral. Like it can be a vertical fold, right? So the fold can also be like this. It can be 90 degrees. And in this case also the fold axis is non-plunging because it is neutral fold. Neutral fold will not be classified as plunging and non-plunging fold, right? So in that case, the amount of dip of the bed, it can either be 0 degree or 90 degree, both. In this case, the dip of the bed is 0 degree. However, in this case, the beds are also vertical, right? So option A and option D both are correct. Okay. Question number 5. An open fold may appear to be isoclinal fold when viewed in a section. Option A, at a low angle to the fold axis. Option B, at 45 degrees to the fold axis. Option C, perpendicular to the fold axis. And option D, parallel to the axial plane. So an open fold may look like this.
Answer B.
Answer B, I guess, if a plane, say for example, if I cut across this in an angle 45 degree, like this, that means this angle is, if this is fold axis, then you are saying that this angle is 45 degrees. So what we will get, the exposure of this limb on this surface will be like this, and exposure of this limb on the surface will be like this. So it will not be an isoclinal fold. It will be a general fold with interleave angle which is lesser than an open fold. However, if we cut a section which is at a very low angle to the fold axis, say for example we cut along a section which is like this, so in that case you will see some section like this. So the more the gentle of this slope, the more isoclinal it will appear. Now if I have a purely vertical, I mean horizontal section like this, what will you see? You see two parallel beds, right? So the more the shallower the plane of intersection, the more the isoclinal the outcrop will become. The shallower the plane of intersection, more the outcrop pattern becomes isoclinal. However, if you cut a section which is at 0 degree or parallel to the fold axis, will not have the hinge. Right? If you just cut along this plane, you will not get the hinge. The hinge is supposed to be like this in any form. But if you just see here at a low angle section, you will just find the hinge. And in that case, the fold will appear as isoclinal. So option A is correct in this case. That means you need to have a very shallow plane of intersection, which makes a very shallow angle with the fold axis, not high angle as high as 45 degree or even higher, at least 10 to 15 degrees angle with respect to the fold axis, and you may get a proper section that will look like an isoclinal fold.
Sir, in
Okay.
isoclinal,
Yes.
sir, in isoclinal fold, the fold limb should be parallel.
Yes.
Yes.
Ideally, it should be parallel, but
In this case, the limbs are parallel.
yeah, in this case, the limbs are parallel because you are cutting across a very low angle section. It is appearing as parallel, but it is not parallel. And even if you cut perfectly horizontal sections of, uh, I mean, not perfectly horizontal, if you cut parallel to the fold axis, you will not get the hinge. You will just get two parallel strips, right? In that case, you won't be getting any fold or closure of the fold. So as long as you have a closure and the beds are appearing to be parallel, not exactly parallel, that would require a very shallower intersection with respect to the fold axis. If you cut very steep section with respect to the fold axis as an angle as high as 45 degrees, you will get diverging limbs and eventually you can calculate the interleave angle. Theoretically, an isoclinal fold should not have an interleave angle, right? Because the limbs are parallel. You can have that if you cut section parallel to the fold axis, but then in reality, if you see that in the outcrop scale, you won't recognize that it's a fold. You will just find it to be two parallel bedding planes. So that is the point. You have to have a section which is at a very low angle to the fold axis, such that you can also contain the hinge zone of the fold, not only the limb but also the hinge zone, and that's how you can identify whether this kind of fold is, uh, I mean, it is actually an isoclinal fold or we are seeing some oblique section with respect to the fold axis. So that is also important to note. So my opinion is that in the field, just looking at the exposure, if you are finding any fold, don't rely on the profile of the fold just observing from the, I mean, you also have to account for the plane of observation that you're actually seeing. So you have to question yourself whether actually I am seeing the profile section of the fold or is it on some oblique section which is deceiving us in the form of this kind of fold. Say for in this case, the regional fold is actually open. But in a section, you are seeing that the limbs of the folds are parallel. And if you just write in your report that, okay, so the fold is isoclinal, that would be a wrong interpretation of the regional geology because you didn't account for the section you are looking on, the fold. So always, in my opinion, you take you take measurements from at least 3 to 4 different sections from the exposure, calculate the plunge of the fold axis, the attitude of the bed, plot them, and from the stereo net you calculate the interleave angle and the plunge of the fold axis and so on. Then you will get a reliable estimation of the data rather than just observing from the field, don't knowing that in which section are you looking. And always while taking some structural data, so you found some traces of bedding planes and you tried to measure it, then the thing is that you should always take the attitude of the plane in which you are also observing. Say we 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 have seen a fold in a field in a particular section. If you just blindly take the data of the interleave angle and the folds and etc. without accounting for the section we are observing, without having a proper measurement of the plane on which we have seen the fold, that would be a wrong interpretation of the structure. It may be right, but we cannot be sure. So that is not to say wrong. It should be an uncertain measurement of the structure. So therefore, you should always also measure the plane of observation, the orientation of the, even if you're just having a quartz vein or some mineral lineation, any kind of thing you are observing. For lineation, you just need trend and plunge. But however, you should also measure on which plane you are actually measuring the plunge, right? Because in that case, what would happen, if that plane is not bedding plane, it is some oblique section, you will get the wrong plunge amount. That would be an apparent plunge amount. So you have to also account for the plane of observation. Together, plotting all the data in StereoNet, you would actually find in which plane or in which plane the mineral lineations are actually falling. So that will be your foliation plane or bedding plane, whatever. And then you cancel out the plane of observation that you measured the data from. So this is the proper or appropriate approach in field observations, in case of field observations. So we also have another course as Introductory Field Structural Geology by Professor Shantanu Mishra. And we also discuss these kind of facts about measuring structural data in the field. These kind of things are also in the course as well, and I also encourage you to enroll for the course. Just you can see the course content, and in that course we also have tried to explain how to carry out a structural lithostructural mapping in a complexly or polydeform terrain. We also talked about the fundamentals of uh, structural attributes, their geometric relationship, different kinds of fabrics, and how we interpret the regional fold from observing the planar and linear fabrics from different exposures. So that is the overall content of the course. And we did field work in Shinhung Shear Zone, and the course is also offered by NPTEL. So it is a complementary course to the theoretical structural geology, but it serves the purpose for field specialists. Okay, so moving on to the next question. Question number 6. Which of the following statements regarding transposition of deformation is true? Option A, transposition foliation is an indication of superposed folding. Option B, stratigraphic information is retained in transposition structure. Option C, transposition foliation develops parallel to the axial plane of the tight folds. And option D, fold closure can be well identified in transposition structures. So transposition means the change of orientation of different feature, say a planar feature or a linear feature, with progressive deformation. So it is transposing. So transposition means the change in orientation of planar or linear fabric with progressive deformation. And transposition is also the mechanism for producing rootless intrafolial folds. Is responsible for producing rootless intrafolial folds. Right. So in this case, you can see that beds have transposed from one layer to another layer. So the deformation is so intense that in one direction you are producing so much deviatoric stress that things are getting flattened out, and these are transposed to a different orientation altogether. Right? So this is the axial planar cleavage. Of course, this is the bedding plane, and you are deforming continuously, and you are producing consecutively tight folds. So the foliation that will develop because of this tightness or subsequent flattening, this will obviously be parallel to the initial cleavage plane, right? So if these are the traces of the cleavage plane, the more the tight folds are becoming, it will be parallel uh, eventually it will be mixed with the existing foliation plane, right? So that means option C is the correct answer for this case. Transposition foliation develops parallel to the axial plane of tight folds, because you are producing so much intense deformation, right? So these are your initial uh, cleavage planes, and you are folding the layers. Now you are continuously folding it. What will happen? The layers will be folded tight enough. This was your initial cleavage. The cleavages will remain. However, this tightness will develop another set of cleavage like this, right? So these are your existing cleavage, and these are transposed foliation. Now, with more further deformation, what will happen? This entire packet of fold, this will tear up from the existing. That they will be losing this uh, interlayer. I mean, they will lose their cohesion from this cleavage boundary, and eventually they will remain inside the cleavages as this highly tight folds like this, right? So due to intense deformation, this produces intrafolial fold. So this is an intrafolial fold. So this diagram was taken from the notes of J.P. Burg of ETH Zurich. So this is how the intrafolial folds are formed. Transposition is the basic mechanism, and transposition also produces the foliations that are parallel to the axial plane of the tight folds.
Sir, in the magmatites, we can say it's as interfoliar fold.
Migmatites, I think migmatites are hard to say because uh, in general, migmatite has this kind of leucocratic and melanocratic textures that are because of high temperature fractionation, and the the folds that we generally see in migmatites are generally pigmatic folds because of their extremely high viscosity contrast. They often fold in single layers disharmonically, but what happens is that the mm, I guess you can say that the link between two different layers of folds is pretty less in case of migmatites because of their high viscosity contrast and uh, very high ductility, because it also occurs in very high temperature. So The disharmonic folds, I guess that is not an example of I mean, disharmonic tigmatic folds are not an example of transposed intrafoliar rootless folds. But you can see intrafolial folds pretty well in calc silicates, especially if you see in the Ambaji region, in the South Delhi fold belt region, we will find excellent outcrops in Rajasthan and in Gujarat, where you can find excellent intrafolial folds in rootless folds in
I mean,
calcilicate rocks.
I've seen in calcilicate. That's I've just asked.
Yes,
I've seen in North Delhi fold belt Khetri basin. I've seen
yeah,
calcilicate.
yeah. There are in the North Delhi fold belt. Even I also did some field work in the South Delhi fold belt, and so the thing is that the concept is it also depends on the rock type you are observing, because what happens in calcilicate, that why calcilicate preserves so much of these structures than seeing in other rocks, because the carbonate part basically erodes away because of weathering, and the remaining quartz part, it's hard and it preserves the structure with so much uh, grooves in it. So that is very beautiful to look into the structure. And also thing is that uh, calc silicate has these two phase components, so that creates a viscosity contrast within the rock that helps in producing the interfolial folds and different high competency structures. That is number one. Another thing is that the more nearer you are to the shear zone, you will find these kind of structures more. And we also seen that whenever we are moving towards a major shear zone, like the Rakhavdev lineament in the South Delhi fold belt, or even nearer to the Fulat shear zone. So the things that if you follow these structures, microstructures, and from the small scale exposures, you will find that the nearer we go to the shear zone, we find these kind of structures, interfolial folds, and sheath folds are also very much common in case of calc silicates. So calc silicate is a beautiful rock to study for outcrop scale. It is very good, but in thin section you won't find. I mean, not much to look into a thin section of calc silicate rocks, because we can't find any crystal plastic signatures. Very few, but the thing is that when you have a thin section, and if you have phyllosilicate content high in that rock, so you will find excellent features in the thin section like folds, and even if you have quartz ribbons, then you will find the undulose extension and recrystallized grains and all kind of features like subgrain rotation, bulging recrystallization, grain boundary migration. These kind of things are pretty well studied in quartz. However, calc silicate rocks are not that interesting when you observe them under microscope. They are only good as an example of classic structures when we see in the outcrop scale. I prefer that if one has to understand the microstructure and crystal plastic deformation, one should look for uh, metapelitic rocks and cysts, because they have high content of quartz. Also they contain high concentration of phyllosilicates. Phyllosilicates preserve these shear bands and cleavage planes, and the microlithons are being defined by the quartz, and the excellent microstructural features are visible only in quartz and feldspar as well. Okay, so question number 7: which of the following condition describes a reclined fold? Option A: plunge of the fold axis is equal to its rate. Option B: plunge of the fold axis is equal to the apparent dip of the limbs. Option C: plunge of the fold axis is equal to the dip of the axial plane. Option D: plunge of the fold axis is parallel to the strike of the axial plane.
Answer A.
Answer A: plunge of the fold axis is equal to its rake. Yes, just A and nothing else.
And C fold.
Exactly, A and C. A and C both are correct options. So recline fold is by definition, this is the actual definition of a recline fold. So recline fold is also a neutral fold, right? Because the plunge of is equal to the deep of the axial plane. So this is a general definition for neutral folds. Plunge of the fold axis is always equal to the deep of the axial plane. So this is how we define a neutral fold. And now if we see a stereographic projection, if this is your axial plane, now in order to produce a plunge amount that is equal to its deep amount, the fold axis has to lie along the deep direction of the axial plane, right? Then only it is possible. So it is only possible when the um, fold axis is plunging along the deep direction of the axial plane. So this will be the fold axis, and this is your deep direction. This is deep amount. This is your plunge amount, and this is the rake, right? But actually, rake should not be equal to the plunge. No, this is wrong because rake is always 90 degrees. Rake should not be equal to the, because even if we have shallower limb, a shallower axial plane, the direction will remain the same, but the amount will change. Plunge amount will be equal to the deep amount. And since the trend is towards the direction of the axial plane, it will always, by definition, have a rake of 90 degrees. So option A is not correct. Option C is only correct because in that case, the rake is not important. The plunge amount and its trend is important. If the trend of the lineation is parallel to the deep direction of the axial plane and the plunge amount of the lineation is equal to the deep amount of the axial plane, then only it will be a reclined fold. Otherwise, it will not be a reclined fold. Right? And in that case,
Means
rake will not be
in
consistent.
A, what will be the condition when A will be fulfilled? Condition A will be fulfilled.
A recumbent fold, because if you have a recumbent fold axis is horizontal. The deep of the, so the horizontal fold will have, uh, I mean, the only the only case it will be, um, because fold
If
axis,
like
if the fold is recumbent, then only it will have the plunge amount with, as equal to its rake, right? So if I just put the fold axis on the periphery, anywhere on the periphery, that would count as your rake as well as the plunge, because it physically doesn't mean anything. You are talking about a horizontal line lying on a horizontal plane. So any orientation you take, it would be remain the same. So in that case, rake and plunge won't mean anything separately. Did you get my point?
okay. That will be in stereographic. It will be in periphery. Then this
Yes, it will remain in periphery since the plunge and the rake will be the
is
same.
equal. Then they comment.
Hmm, exactly. Okay. So question number 8. High angle intersection between bed and foliation indicates option A, limb of a recumbent fold, option B, limb of a tight fold, option C, hinge of a fold, and option D, limb of an open fold. So if I have a fold, and these are the traces of the axial plane. So at the hinge, if you see, the angle of intersection between bedding and cleavage becomes maximum. Approximately 90 degrees. So at the hinge zone, the cleavage and the bedding are perpendicular to each other, and that is how if we find at any exposure that the bedding plane and cleavage planes are showing orthogonal relationship, that means you are standing on the hinge of the fold. So high angle intersection between bed and foliation indicates hinge zone of a fold. So option C is correct. So what is the difference between the term that we commonly use as a proxy to each other? So one is axial plane and another is axial planar cleavage. So what is the exact difference, do you think, between these two terms?
Axial plane, axial plane is the plane which is passing from the highest point of curvature,
Hmm.
and axial planar cleavages are the sympathetic to that axial planes, which are either side of hinge on.
Yes, that is correct. But the thing is, you have to remember, axial plane is actually an imaginary plane that
Yes,
does not exist.
that's what
Whereas
cleavage actually.
a cleavage plane that is defined by mica and other weak minerals that are developed during the fold, which are characteristically parallel to the actual axial plane, is called the traces of or is called axial planar cleavage, because it is a cleavage plane that is, because it is those are the weak planes that are defined by presence of mica. They are divided into cleavage and microlithon domain. But this time, the axial planar this cleavage is actually following the axial plane of a fold, and that is how even we don't see an actual axial plane in the field, because we can't observe that it's an imaginary plane, but we do see planes that are actually parallel, geometrically parallel to each other, and therefore we also call them axial planes, because actually those are not actual axial planes. Axial plane should be only one axial plane. A fold should only have one axial plane that is passing through the hinge. That's it. That's an imaginary plane. But there are infinite number of planes that are parallel to those that axial plane, and those are the traces of this axial. Cleavages that are being developed.
Sir,
So that is, yes.
sir, sorry to this,
No, no,
interrupt you.
yes,
If it's such a condition when axial plane is curved, then the traces of
yes,
axial plane cleavages are also curved, or it may be in straight line. But it may be
no,
follow.
yes. That will also curve. That will also curve, but in field you won't see the curvature. So if you are just doing in a regional scale field, you won't see the curvature. But what you will see that the attitude of the deep of the axial plane, the attitude, strike and deep of the axial plane, the cleavages, they should constantly change, and not only the deep attitude of the cleavage planes, but their intersection angle with respect to the bedding plane, that would also change. And that's how we just gather the data, and even when we plot eventually, we see the stereo net and comment on the thing that whether the fold is uh, planar, cylindrical, non-planar, non-cylindrical, cylindrical, non-planar, that kind of things.
Hinge
So we just,
in a hinge zone, the
yes,
the relation of bedding plane with this axial plane cleavage is always changing as we move from right limb to left limb or east limb to west limb. If some portion a north-south fold is there, if we are moving
Uh,
from east to west in the hinge part, the relation of this
hmm.
axial plane cleavage is always as we move, we see that the axial plane faces are different relations with this bedding plane.
Yeah, in case of a non-cylindrical fold, right?
Non-cylindrical.
Yes, yes, yes. It would change. It would change. So you will just see that if you walk along the trace of the axial plane of the fold, you will get different plunge amount of the fold axis. Not only the plunge amount, but also the trend. You will see oppositely plunging fold axis in a location. So that's how you will identify that. Okay, so there is a superposed. There has to be a superposed deformation because um, without the existence of a superposed deformation, you cannot actually theoretically produce a non-cylindrical fold. There has to be some sort of interference pattern, because if you just follow ideal buckling process or flexural slip, whatever, you will not be finding
Right, right.
non-cylindrical folds. You'll always find cylindrical folds, and specifically class 1B type of fold through buckling and flexural
Right,
slip.
right, right. Only if one thing will operate, then we get only cylindrical.
Exactly. Cylindrical class 1B type of fold. But there has to be some non-coaxiality to actually produce non-cylindrical fold. Not actually non-coaxiality. There has to be some superposition. Even for superposed deformation, you can find coaxial superposition. In that case, the fold will be cylindrical, but it won't be. Uh, it will be non-planar. No, actually, non-planar cylindrical is not possible.
Not possible. Not
Yeah, yeah, not possible. It should be planar non-cylindrical. Yes, it should be planar non-cylindrical in case of coaxial superposition, and if you have non-coaxial superposition, it will be non-planar non-cylindrical. That's all. Okay, so moving on to the next question. In a syncline, all rock layers, option A, deep towards the fold axis, deep away from the fold axis, have vertical dips and have horizontal dips. It's a very
A,
easy
A,
question.
A,
Option A. Yes.
A.
Yes. There's nothing to discuss more about, but just for the sake of thing. So a syncline will have this kind of structure. So progressively younger beds. And if this is the fold axis, the beds would be towards the fold axis.
पानी में
Okay. Question number 10. Interleave angle and shape of a fold is best studied in a section parallel to the plunge of the fold axis. Option B, section containing the pole of the bedding planes. Option C, section parallel to the pole of the axial plane. And option D, none of the above. So this is
what do you mean by pole of
pole of what?
pole of axial plane?
Exactly. That is why I'm drawing this. So if I have an axial plane, the pole of axial plane would actually mean two different limbs. I mean, not two different limbs. So this will be the pole of axial plane.
Okay.
Plane means a vertical line perpendicular to the fold axis. Right? So this is pole of axial plane. So if I section parallel to the pole of axial plane, that means this section, right? So this will be a section parallel to the axial plane. So the thing is that apparently it seems if we cut a section which is parallel to the pole of the axial plane, we might get the interlimb angle. But it is actually not the case, because here I have drawn a vertical axial plane. So if vertical axial plane for a symmetric fold. Now consider that we have a fold which is like this, and it has a shape like this. So the axial plane would dip right away like this. So a section for the pole would cut across the fold like this, right? So in that case, you won't be able to calculate the interlimb angle. Now also there will be a dip of this plane. So that plane would not be perfectly perpendicular or vertical. And in that case, you will not be able to measure the interlimb angle. The best option you can get is to get the plane containing the pole of the bedding planes. So if you join something which contains all the pole of the bedding planes, you will eventually end up having a section where you can find the interlimb angle. Will provide the interlimb angle. Okay, so this was about the 10th question. Question number 11 says that in Ramsay's fold classification, class 2 fold is characterized by option A, core converging deep isogons, option B, parallel deep isogons, option C, core divergent deep isogons, and option D, uniformly inclined deep isogons.
A, core converging device.
In class 2 folds, right? So if I see class 2 folds means the deep isogons are parallel.
Sorry.
So class 1 fold will have core converging isogons, class 2 fold will have core parallel deep isogons, and class 3 folds will have core diverging deep isogons. So this is the fundamental classification. And then we will have, based on the thickness of the limbs, we will have three different kinds of class 1 fold. And by definition, if you are having divergent or parallel deep isogons, the thickness of uh, the layer thickness will automatically change from hinge to limb. So that's why we don't consider the thickness variation in case of class 2 and class 3 folds, and further subdivide them into different categories. But for deep isogon which are converging, then also there can be three different scenarios. So class 1b fold is called parallel fold, right? So parallel fold is not associated with parallel deep isogons. In fact, parallel deep isogons create folds that are known as similar folds. Right? Why class 1b fold is called parallel fold? Because the layer thickness remains same in every point. So that is why the layers are parallel to each other, remain parallel to each other at every point when we draw the deep isogons. And that is why we call them parallel folds. Class 2 folds have similar curvature, similar outer and inner arc, similar curvature in outer and inner arc, and that is why we call them uh, similar folds. And for class 3 folds, there is a diverging kind of deep isogons, because not only the layers are have different thickness, but curvature of the inner arc is lower than the outer arc. Right? So curvature of inner arc greater than curvature of outer arc. This scenario will produce class 1 folds. Curvature of inner arc equal to the curvature of the outer arc. This will produce class 2 folds. And eventually, curvature of inner arc less than outer arc. This will produce class 3 folds. So this is how, based on curvature as well, you can all remember the Ramsey's classification. Okay, so moving on to the next question. Joints perpendicular to the fold axis, which are common feature in orogenic belts, are commonly known as option A, columnar joints, option B, release joints, option C, extension joints, and option D, cross joints. So
Tension joints.
these are actually no, these are called the cross joints. So if you have fold,
Cross joint.
yes. So folds, if you have folds like this, and these are your fold axis. So joints that will form following the curvature of the folds like this, they will segment the folds in different layers like this. That kind of joint is called cross joints. So these joint sets, cross joints, they cut across the fold. So that is why these are cross joints, the crossing across the fold. And these folds are, these cross joints are perpendicular to the fold axis. Okay, so option D is correct. In question number 11 is a parallel deep isolines. Okay, so question number 13. During layer parallel compression, two layers of stiffness ratio of 1.5 with thickness of 2 and 4 centimeter respectively produces buckle folds in a rock. The ratio of their wavelengths will be 1, 1 by 3, 2, 1 by 2. So the length, the wavelength to height thickness ratio is 2 pi cube root over of mu 1 divided by 6 mu 2. This is the buckling instability equation. Right? So mu1 by mu2 is 1.5 approximately. The viscosity stiffness ratio or the viscosity contrast we can consider as 1.5. So L by H is equal to 2 pi cube root over of 1.5 by 6. So this will be constant, this term, 2 pi cube times half. So for layer 1, L1 by H1 is equal to 2 pi cube times half, or L1 by, if the layer thickness is 2, then L1 by 2 is equal to 2 pi cube by half. And for layer 2, L2 by H2, right? So L1 by L2 will eventually cancel out as 2 by 4, right? Because L1 by L2 is equal to H1 by H2, right? So you will get half. So the wavelength ratio will be option D, 1 by 2. Okay, so moving on to the next question. In a zone of superposed folding, poles to bedding plane show a great circle distribution. For such a case, the fold axis related to the first generation of folding will be option A, also be distributed along the same great circle girdle. Option B, be distributed on a great circle girdle orthogonal to the bedding plane girdle. Option C, shows a cluster around the pole to the bedding plane girdle. And option D, shows a small circle distribution around the pole to the bedding plane girdle. Okay, so if I have a stereo net and if I see that the poles to the bedding plane, they are following a great circle like this. So this is north, this is south. Poles to bedding plane follow a great circle, means the fold surface is uniform. Hence it is cylindrical. So this is a signature of a cylindrical fold that the poles to the bedding plane, they will always lie on a single great circle with high, very less scatter. So if there is a very high scatter and deviation from the expected bedding, great circle, then the fold is never cylindrical. It is always non-cylindrical. So this is the test to actually study whether a fold is cylindrical or non-cylindrical. You just measure the poles to the bedding plane from one limb to the other limb. You plot them on a stereo net, and if you just have the data being going through a great circle with very less scatter, that means the fold is overall cylindrical in nature. Now in that case, this plane, this great circle, is the profile plane of the fold. And the pole of the profile plane is the fold axis of the fold. So in reality, when you plot some data for a cylindrical fold, you will see that the pole to this profile plane will have again a small cluster of data points that generally will represent the fold axis. So you measure the average plunge amount from this data and their orientation, and eventually you will get the orientation of the fold axis. So this is how we determine the nature of cylindricity of a fold. If the fold axes were being distributed along a small circle along like this, then there would be a possibility of having uh, non-cylindrical folds. So in this case, option C will be correct, because for a cylindrical fold, it will always show a cluster around the fold to the bedding plane girdle. Okay, so
Okay, sir.
this is our last question. This is not directly related to folding, but it's related to field observations and outcrop patterns as well. So if angle, if the slope angle of the ground surface is more than the deep of the bedded sequence and both the grounds and beds are inclined in the same direction, then option A, younger beds will be made within the direction of the dip. Option B, older beds will be made within the direction of the dip. Option C, younger beds will be made at the opposite direction of the dip. Option D, only the oldest bed will be made it as one goes in the direction of the slope. So
It
say
will
this
be
is my
the
horizontal line, and these are the bedding planes that they are having a very shallow dip,
answer will be B. B.
and we are cutting across with higher slope, right? Uh, say so this is my slope and these are the bedding planes, right? So this is the Yonging direction, of course. So this means older bed. This is oldest, and this is youngest, right? So if we go down the slope in the direction of the dip, yeah, we will find older strata as we go along the direction of the dip. So yes, option B is correct. Older beds will be made within the direction of the dip. Yes. So this was the live session for week 8. Uh, do you
Sir,
know
week,
in the week
sir,
what is in week 9? The week 9 contents are released, right?
yes, release, but we have not seen, sir, yet.
Okay, 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 no problem. I will. It is also mentioned in my slides as well. I just remember.
First
Yeah,
slide I have missed.
yeah. Budinaj and related structures. Yes. So we will be talking about Budinaj and formation of Budinaj. We already did some problems related chocolate tablet Budinaj and flint diagram. So we will repeat those things again. The formation and mechanism of Budinaj. Okay. So if you don't
Sir,
have any doubt, then yes. Say.
if you will provide your mail ID, possible, if you allow.
Okay. Yeah, yeah. I'm writing my email ID. You can note it down. So this is my email ID. Okay. Thank you, and we will meet again in the next discussion session. Okay. So I am closing this meeting.
Okay,
Bye.
thank you, sir.
Hmm, thank you.